Okay, this is 5.3a, College Algebra, Matrices and Systems of Equations, page 462. Okay, at this point, with systems of equations, you've learned how to solve systems of equations in two variables, such as this one here. And one of the things that you do when you solve a systems of equations is you just worried about the number that was in front of the variable. You change, let's say you change this to a -2 so that you could add those together, but the x's and the y's just kind of drug along with you. So all you really messed with were the numbers. So in this section, we're going to learn how to just worry about the numbers. So one of the things we can do is we can make a little bracket here and put a 2 and a 1 here, a -3 and a 4. We're going to do a vertical line for our equals, a 7, a -2, and then we're going to end it with a bracket. Okay, that is called a matrix. In fact, this one in particular is called an augmented matrix because it includes the coefficients, the 2, the 1, the -3, and the 4, as well as the constants, the numbers without a variable. So that's called augmented because of that. Now, if we just use this here, the 2, -3, 1, and 4, and made our square bracket here, and just had these four numbers there, that would be called a coefficient matrix because all it includes is the coefficients of the variables here. So it would be a coefficient matrix. Okay, so as we continue on with some definitions here, we have rows to our matrix that are horizontal, and we have columns. And if we want to name this matrix, we name it according to the rows by the number of columns. So if we had a coefficient matrix like we had here, that would be called a 2 by 2 because we have 2 rows by 2 columns. And that's not only the name, it's also called the order of the matrix. The order of the matrix is 2 by 2, 3 by 2, 4 by 6, however many rows times the number of columns. If we were to look at the augmented matrix that we started out with up here, this is going to be a 2 rows by 3 columns. It's going to be a 2 by 3. Okay. When the number of rows and columns are the same, it's called a square. The matrix is a square matrix. So whenever the order is the number of rows times the number of columns is the same, it's called a square. All right, so the 2 and the 4 are called the main diagonal. Okay, so we don't necessarily have a minor diagonal or anything, but we have a main diagonal, and it always starts with the top here and moves this way down the diagonal. Okay, and the numbers, each one of these numbers are called entries. Okay, so a lot of definitions there that you should have in your notes because I'm going to assume on a test when I say something along the line of what is the order of this matrix, you're going to need to know that it's a 2 by 2, or in this case a 2 by 3. Okay? So, Gaussian elimination with matrices. In section 5.2 we learned how to use the Gaussian elimination when it came to a system of equations with 3 variables and 3 equations. And what we're doing basically is the same kind of thing here. What we're using matrices for is to, let's get some of this out of the way here, is to solve systems of equations. So for example, if I have 2x minus y plus 4z equals -3, and I have x minus 2y minus 10z equals negative 6, and I have 3x plus 4z equals 7, I can rewrite this as an augmented matrix. So I can go and make this, draw my equal sign, put a negative 3, negative 6, and a 7, a 4, a negative 10, and a 4, a negative 1, a negative 2, a 0, because there isn't anything there, a 2, a 1, and a 3. So that is an augmented matrix. What I'm trying to do, if you remember in section 5.2, we started off with an x, a y, and a z. And then we got rid of one of the variables and made life a little bit easier. So let's say, for instance, we got rid of the x. So in the when we got rid of the x, we had two equations with just a y and a z, and we put those together so that we would just have one letter representing the number. So that's kind of the format that we've got here, is a column or a diagonal right here, which is my main diagonal, and then we have this term or these two variables and this variable right here. So that's what we're trying to do with the problem that I have written up here. So our goal is to find a row equivalent matrix in such a way that it looks like, when we're done, let's just bring that up there, I want the matrix to look like this. And again, we're talking augmented, so we've got that equal sign. I want the first term to be a 1, first term in the second row to be a 0, in the third row to be a 0. So remember my example I had over here. Just look real quick right here. I had an x, y, z, a y, z, and a z. So I'm trying to get the same thing. So in order to do that, I've got an x, a number, a number, a number. I have basically a y, a number, and then I want to get rid of my y, and then all I have left is a z. So see what happens there. I have all three variables, two variables, down to one variable. And the only way I can do that is to make these zeros and these ones. Okay. So what I'm going to try to do is I'm going to try to take this matrix and make this ones, because see, my diagonal makes them ones. This, and this zeros to follow this here. Well, this is already a 0, so that's good. Okay, so I need to make these zeros, this diagonal ones, and then these numbers here are going to be my answers. This is going to. So let's go through the procedure in order to do this. So I'm going to erase this whole page, and I am going to rewrite this here, and we will see if we can make it look like this. So again, our main diagonal are going to be ones, everything to the left is going to be zeros, and then this here, these can be whatever they end up being. So there's a method to doing this, and that's what I'll show you next.